Energy is something that all life relies on. This video is a deeper dive on a form of energy that could be a solution to our energy requirements in an ever-growing world and beyond. The concept of fusion energy has been circulating since the dawn of the nuclear age in the mid-1900s, which was spurred by the technological advancements of World War II. As traditional energy sources dwindle, fusion energy has gained increased traction over the past few decades. Fusion energy harnesses the power of nuclear fusion, which involves fusing two relatively heavy atoms, typically heavy hydrogen isotopes, known as deuterium and tritium. This process requires immense heat or pressure to force the atoms together. Fusion is a natural phenomenon, prevalent in large stars, where pressure is far greater than on Earth. To achieve controlled fusion on Earth, two primary methods are employed: magnetic confinement and inertial confinement fusion, which uses lasers to heat and compress the hydrogen atoms.
While the mechanics of fusion energy may seem foreign to many, its underlying principle is rooted in an equation familiar to most high school students: E equals mc squared. Energy equals mass times the speed of light squared, the brainchild of Albert Einstein. Fusion energy production aims to efficiently convert mass into energy, hopefully generating more energy that is consumed in the initial process. However, for this process to even get started, protons need to overcome something called the Coulomb barrier, which is a repulsive force that keeps likely charged particles apart, kind of how like two sides of the same magnet repel each other. This necessitates either extremely high temperatures or extremely dense circumstances, a challenge that the sun itself cannot overcome without its own internal gravity. Unfortunately, here on Earth, we don't really have the gravity of a celestial body to aid in man made fusion, so we have to explore much, much smaller avenues than a sun. Quantum mechanics offers a solution to this conundrum through the concept of quantum tunneling. Under immense pressure, particles can tunnel through the Coulomb barrier, even without reaching the extreme temperatures that would otherwise be required for fusion. This delicate balance between temperature and pressure allows for fusion to occur, maybe even cold fusion, which is fusion that happens at simply room temperatures. Now, somewhere in here, we should probably explain, does any of this violate the laws of thermodynamics? It almost seems too good to be true, putting energy into a system and then getting infinitely more energy out of it. Thankfully, none of nuclear fusion really violates any laws of thermodynamics. Specifically, Law 1 and Law 2 are some pretty big contenders, which I will explain. The Law 1 is conservation of energy. The total energy of an isolated system must remain constant. In fusion, the energy released is equal to the mass deficit multiplied by the speed of light squared. This means that no matter how much mass you put into a system, you will get that much energy based upon the mass times the speed of light squared, according to Einstein's theory of relativity. The second law of thermodynamics pertains to entropy, which is a measure of disorder or randomness. The second law states that entropy tends to increase over time in order for everything to start equaling out. In nuclear fusion, the initial state of separate nuclei has lower entropy than the final state of a single, heavier nucleus. This increase in entropy is a driving force for the fusion reaction. Now, what this means is that in the initial state, when nuclei are smaller, they tend to be in a less volatile state. And then once they're all crammed together in nuclear fusion, they become more volatile, which is what releases the energy. This allows for chain reactions in fusion, like in the sun.
Okay, so now we will be talking about the upsides of nuclear fusion in today's world. One of the most pressing challenges in power generation today is the trade-off between energy output and environmental impact. Existing options either produce meager amounts of power relative to the resources required, or come with significant environmental drawbacks. Nuclear fusion offers a promising solution by addressing both of these concerns. The waste product of nuclear fusion is harmless water, simply H2O, and the amount of energy generated is 20 to 100 million times greater than that produced by chemical reactions from fossil fuels. This remarkable potential suggests that if fusion can be harnessed, it can not only meet our current energy demands, but also provide abundant power for future terrestrial expansion and even extraterrestrial ventures such as spacecraft propulsion. So, with all this upside, why isn't this already in use? Despite the immense promise of fusion energy, a nagging question still remains. Why haven't we yet dotted the globe with large-scale fusion reactors? The success of a fusion reactor conjures the images of a world where energy troubles are a distant memory. However, simple reality is that creating the conditions for sustained fusion reactions is an energy-intensive endeavor. The primary challenge facing engineers and scientists who work in this field is crafting an environment where fusion reactions consistently generate more energy than they consume. Researchers are tirelessly exploring avenues to reduce power input through more efficient confinement processes and even harboring hopes of discovering a Today, many projects and experiments are taking place in the efforts to harness the net positive fusion energy that numerous researchers are destined to achieve. The forefront of fusion energy research lies in southern France, where the International Thermonuclear Experimental Reactor, or ITER, project is taking shape. The ITER project consists of 7 international members and represents the most advanced fusion research reactor tasked with achieving sustained nuclear fusion in a net positive energy state. They seek to do this using the tokamak system, which uses a device that confines plasma through a magnetic field. This is projected to produce several hundred megawatts of power and have a net fusion gain of 10. With this project underway, it will provide scientists with invaluable insights into the behavior of matter under the extreme conditions required for fusion, paving the way for replicable fusion reactors that could power cities and revolutionize the world's energy landscape.
While fusion energy holds immense promise, scientists are laying the groundwork for its viability in the mid-2050s. Recognizing that harnessing the power of fusion reactors remains a long-term endeavor. Yet several hurdles must be overcome to accelerate this journey. A significant challenge lies in securing adequate funding for reactor development and research. Fusion's distant horizon and uncertain outcome often steer funding towards immediate energy solutions like solar or wind, inadvertently delaying the realization of a sustainable long-term solution to our energy problems now and in the future.